What's up, guys? It's Dan from SageMathTutoring.com, and here I have a few problems that one of my students, or at least the kinds of problems that one of my students is going to have to face for an upcoming test. So one of the things I like to do is provide YouTube videos to help my students out based off of the problems that they will soon have to face on a test, so that my students could use this as a study guide. So that's what we're doing right here. And it looks like we have about 12 problems. I've labeled them A through L. And let's get right to it. So what we see here is clearly 5 over 6 minus 1/3. When you are subtracting or adding fractions, you need to have a common denominator. Clearly, we do not have a common denominator here. So we need to make sure that we have a common denominator, and the way to find a common denominator is you ask yourself, what is the least common multiple of the two numbers down here? Now, a multiple is a number that both numbers divide into. Now, it so happens that the least common multiple of 6 and 3 is actually 6, because 6 times 1 gives me 6, and 3 times 2 gives me 6. So we could actually leave this one alone. We're going to have to sort of mess with this fraction in order to get that common denominator. And the way that we do it is by multiplying this bottom number by whatever it takes to turn it into a 6. In this case, it would be 2. You can't just multiply the bottom by 2. You have to also do the top by 2 as well. So we're going to do that right here. On the next line, I'm going to rewrite what our situation is. We've got 5 over 6. And then over here, it's a multiplication of two fractions. We've got 1 times 2, which is 2, and 3 times 2, which is 6. So this ends up becoming 5, 6 minus 2 over 6. And at that case, or when you get this far, you just keep the denominator and you subtract the numerators. So we end up with 3 over 6. Now, this is the correct answer. However, your teacher is probably going to want you to reduce any of your answers as much as you can. And it so happens that 3 over 6 is equal to 1/2. So that would be the final result that I would show to the teacher. All right, moving on to the next. Okay, so this is a big old mess. First of all, obviously there's exponents going on, which could be a little bit confusing. There's also a bracket and so on, division of two fractions. So this whole thing could be a little bit confusing, but basically at the very least, you want to remember that you want to use PEMDAS. So in other words, take care of what's inside the brackets or parentheses first before doing anything else. So what we're going to do is we're going to simplify all this stuff in here. And when I say take care of what's inside the brackets, I mean simplify it as much as you can before you do anything else from the outside. So we have a fraction divided by another fraction. So that's going to be a fraction, hopefully, times the reciprocal of the next fraction. So on the next line, I'm going to rewrite this as b. And I'm just going to write this. I've heard it as keep, change, flip. All right, so we're changing the operation from division to multiplication, and we're flipping the next fraction. Okay, so this is where we are, and it so happens that we could indeed simplify this because basically, let's kind of consider a simpler case. So what we're going to do is we're going to kind of go over here and just investigate a situation where imagine you had a to the 5th over a squared. Well, basically, that's equal to 5 a's being multiplied together all over 2 a's being multiplied together. And this would cancel with that, this would cancel with that, and you would be left with, at the end of the day, you'd be left with a, also known as a to the 3rd, okay? So this would be the sort of simplified version of this scenario. Now, I did it by kind of representing how many a's you've got, multiplied together, and then showing you why it works out this way. But some teachers would rather you just sort of remember that if you have a to the 5th over a squared, you have the same base, a, but different exponents. You can actually keep the base and then subtract the bottom exponent from the top exponent, and you end up with a to the 3rd. All right, so that's another way of thinking about it as well. This is somewhat of a more, I would say, time-efficient way of going about it, where you just, take the top exponent, subtract the bottom exponent, and you end up with this. So that's something to take into account. Now, another thing that I think is worth taking into account is the fact that if you have something like, let's see, if you had something like b to the third all over b to the fourth, well, what is that in reality? In reality, that is a string of 3b's being multiplied together, all over 4b's being multiplied together. And this cancels with that, this cancels with that, this cancels with that, leaving me with this 1b down below. All right. So when we canceled the top row, what actually happened in reality is this turned into, when I say this, I mean the top turned into a 1. And what we have left down below is this remaining b. All right, so that ends up becoming 1 over b. All right, so that's what happens when the exponent on top is smaller than the exponent down below. Now, could we have used that same old trick of the trade that I had mentioned earlier, where you simply keep the base and subtract the exponents? Well, the answer is yes. You would end up with b raised to the negative 1 right there. And that's kind of an interesting situation, because it's like, all right, b to the negative 1. Well, how is that equal to 1 over b? Well, b to the negative 1 could be reconceptualized as 1 over b. And the reason is because anytime you have a number raised to a negative power, that is the same thing as taking this base and shoving it into the basement, turning the sign of the exponent to the opposite, and sticking a big fat 1 up top. All right, so this is actually a law of exponents that is beneficial to remember, and that's essentially what's happening here. This b to the negative 1 turns into 1 over b. All right, so these are some concepts that are, believe it or not, going to be helpful when we're dealing with this scenario. So moving our attention back to this situation, basically we've got this multiplication scenario here. So we're going to have to deal with this. And what we end up with as a result is the following. We're still going to have the b to the third on the outside. But really we have a to the third times b to the third all over a to the second times b to the sixth. Because at the end of the day, this is just a fraction multiplied times another fraction. What do? You multiply straight across. A to the third times b to the third is right here. B to the sixth times a squared is right here. Now, I changed the order so that I could stack the a's directly on top. I didn't really need to do that, but I think it's helpful to sort of understand what happens next. Now, what do we have over here? Well, we have a to the third over a squared. Well, we already sort of discussed what would happen if you had that type of scenario. That would end up becoming a to the 3 minus 2, also known as a to the first power, also known as a. All right, so at the end of the day, this becomes, or not at the end, but the next step would be to recognize that when it comes to this part right here, that just becomes a. Now, we still have the b to the third over b to the sixth, so we could always investigate that situation. We'll do a little section over here. So b to the third over b to the sixth, what is that? That equals b to the 3 minus 6, also known as b to the negative 3, also known as 1 over b to the third. Okay, so really over here, this guy right here, that's going to give us, and I'll actually just keep it 1 over b to the third. Okay, we're going to keep it in yellow. So, and make no mistake about it, this is just a number times another number. So really, at the end of the day, we have three numbers being multiplied together. You have b to the third times a times 1 over b to the third. So what can you do with that? So what we have here is again, b to the third times a times 1 over b to the third. Now, multiplication is commutative, so that means that if you have some number a times b times c, well, that's really equal to b times a times c. So in other words, the order by which you multiply three numbers together doesn't really matter. So what I'm going to do right now is represent this situation in a slightly different order. And here's the order: b to the third, and I'll wrap it in parentheses to kind of keep it partitioned. We have 1 over b to the third, and we have that times a. Now, let's investigate this. Let's start by multiplying this times this first. B to the third times 1 over b to the third. Now, keep in mind, this b to the third secretly has a 1 underneath it. And you know what? While we're at it, this a also has a 1 underneath it. So you could think of this as a fraction multiplied times another fraction multiplied times another fraction. And what do you do with fractions? Well, you multiply straight across. So this first two fractions would end up becoming b to the third, because b to the third times 1 is b to the third, all over b to the third. Why? Because 1 times this b to the third is a b to the third. And that's what we have when we multiply the first two fractions together, and we still have this a over 1 from here that's kind of hanging out. So in other words, we just multiplied these guys and turned it into this, and then we're going to multiply this times that. But here's the deal: b to the third over b to the third. Well, isn't that just 1? I mean, anything over itself is just 1. So in a sense, these cancel out, leaving me with 1 over 1, also known as just 1. So really, it's going to be 1 times a over 1, which equals a over 1, also known as a. All right. So that was a long-winded explanation as to how to deal with this. Let's recap. First, you have to deal with what's inside the brackets. And we did that. We kept this one, we changed the operation, and we flipped this one. That's what we did right here. And then we kept this b to the third on the outside. That's kind of like, he's kind of hanging out. And then you simplify what's going on inside here as much as possible. We had b to the third. We had all this shenanigans going on inside. This ended up simplifying into a times this, right? And we sort of recognize that this is a string of three numbers being multiplied together. We switched the order, so 1 over b to the third is the second number in the string, and we took it from there. Okay, what is the next prime number after 17? Well, I think it helps to get clear on what the prime numbers are. It starts with 2, then it's 3, then it's 5, 7, not 9 but 13, not 15 but 17, 19, not 21 but 23, not 25, not 27, yes 29, 31, yes, not 33, not 35, 37. Let's see, 39 is divisible by 3, so that won't work. Let's see, 41 is prime, and 43 is prime, and not 45, 47 would work. And it sort of goes on like that, actually. Now, you might ask, well, how do I know? Well, I will admit it is in part memorization, at least for the first, few, okay? And then it is another part just experience, recognizing that, a prime number is a number that's divisible only by 1 in itself. And then I also know that this happens to be, 2 happens to be the only even prime number. So I'm kind of using that information where, yeah, I list 2 right out the gate, and then I'm kind of through my thought process going through all the odd numbers in existence. And I'm asking myself, each odd number that pops in my head, is that divisible by, another number other than 1 in itself? If so, it's not prime. So 3 is only divisible by itself and 1. 5 is divisible only by itself and 1. 7 is divisible by only itself and 1, and so on. I skipped 15 because 15 is divisible by 5 and 3. 21 is not a prime number because 21 is divisible by 3 and 7. 25 is not a prime number because 25 is divisible by 5. 27 is not a prime number either because that's divisible by 3 and 9, and so on. I kind of went down the line. But anyway, we want to know what's the next prime number after 17. Well, clearly it is 19, right there. To what set of numbers does 0 belong? Well, I think it helps to think of like a chart of concentric circles where basically you have the following. You have the set of all real numbers, all right? So this would be real numbers, okay? And then within real numbers, you have two different kinds of numbers. You have rational. Handwriting's not that great. And we have irrational. Okay. Now, let's just get this over with. Irrational numbers, that features numbers like pi, like the square root of 2, things like that. And basically, irrational numbers are numbers that, if you were to consider the decimal version of irrational numbers, those decimals would be like 3.172357112. They would go on forever in such a way that there is no predictable pattern. So first of all, they'd go on forever without question. They don't stop somewhere. They go on forever. And they do so in such a way that there is no predictable pattern. Okay, so in other words, 172 doesn't repeat forever. It's not like 172, 172, 172. There's no pattern at all. And that is one way of knowing that the numbers are irrational. Now, it so happens that pi is a famous irrational number. It's usually 3.14 and then a whole bunch of numbers after that, actually. And then radical 2 is a famous irrational number because that ends up becoming 1 point something with all these numbers that go on forever in such a way that do not repeat a pattern. Contrast that with rational numbers, like a rational number would be something like, 0.75, okay? How do I know that that's rational? Well, let's get clear on what rational numbers are, just in general. So rational numbers are such that it's a number that could be represented as a over b, where a is an integer and b is an integer. And an integer is essentially a number that would be on the number line as a tick mark on the number line. All right, so you may recall the number line stuff. Basically, every time you have a tick mark, including 0, that is an integer. So rational numbers are numbers that could hypothetically be represented as a over b, where a is an integer and b is an integer. And basically what that results in is a scenario where if you were to turn it into a decimal, it would always be such that the decimal always ends. Like right here, it ends, right? So the decimal might end, or it would be something that is such that the decimal goes on forever in such a way that repeats a pattern. So anytime you see this bar over the numbers, you know that you're dealing with a rational number, okay? So things like 0.75, things like negative 1.7 would work, etc., etc. Things like, well, let's see, 7.6 repeating, that would work too. Now, within rational numbers is something called integers. So we'll call it int. Integers, I already explained. Those are the whole numbers that are tick marks on the number line. So that includes things like -2, 0, 1, 3, etc. That's integers right there. Now, within integers are what we would refer to as whole numbers. So we're going to call that WH for whole numbers. Now, whole numbers are all the positive numbers, including 0. So 0, 1, and 2. Now, within whole numbers is another category of numbers. And that category of numbers is called natural numbers. So we're going to go N for natural. And that is all the positive numbers not including 0. So that's like 1, 2, 3, yada, yada. All right. So that is a nice chart that should enable us to understand how the different sets of numbers relate to each other. So, what's the question? To what set of numbers does 0 belong? Well, it's definitely not irrational, right? Because irrational numbers have decimals that go on forever in such a way that do not create a repeatable pattern. So what does 0 belong in? Well, basically, it looks like 0, if you look here, 0 does not belong in the natural numbers, because remember I said that natural numbers are all the positive numbers above 0, all the positive integers above 0. So 0 does not belong there. You notice 0 does belong in whole numbers, and 0 does belong in integers. And if 0 belongs in integers, then you know that 0 is a rational number as well, because if all integers are inside rational numbers, then 0 is inside rational numbers as well. So really the answer is the set of numbers would be whole numbers, integers, and rational numbers. And you know what? Let's just say real numbers as well, because let's not forget that everything is inside real numbers. So basically, these are all the sets that 0 does belong inside. Notice how this is left out, and notice how this is left out. All right, write an algebraic expression for 3 times the quantity 2 plus x. So as soon as I see the quantity 2 plus x, I'm immediately thinking in terms of parentheses. Now, I could write it in order that they wrote it, whereas I quantity 2 plus x, but I'm just going to write x plus 2, because it's the same thing, and it's kind of better form to write the x first. All right, so this is the quantity 2 plus x, written as x plus 2. And we want an algebraic expression for 3 times that. Well, that's easy. That's just going to be 3 times that. Okay, that's all there is to it. Okay, so here we have 1/3 times this entire quantity. Now, once again, PEMDAS would suggest that we should simplify anything that's inside parentheses first. So we could definitely do that. We have 3/10 plus 1/5. Now, the problem is, of course, we do not have a same denominator, so we're going to have to do this sort of extra step of finding the common denominator. So on the next line, I'm going to write 3/10 plus, and I'll write 1/5 again, but this time we're going to write a little bit of a space here because I'm using foresight. So we have 1/5. So what is the least common multiple of 5 and 10? It's definitely 10. So I need to multiply this 5 times something in order to give me this 10, because once I turn this guy into a 10, then I'm going to have a common denominator. So clearly 5 times 2 would give me a 10. So I'm going to multiply 5 times 2, but I can't just do the bottom times 2. I have to also do the top times 2. So what that results in is the next line, which is 1/3 times 3/10. plus 2 over 10. And that results in the following. On the next line, it's going to be 1/3 times 5 over 10. And this 5 over 10 right here reduces to 1/2. So we can also rewrite this as 1/3 times 1/2. And when you're multiplying a fraction times another fraction, you just multiply straight across. So 1 times 1 is just 1. I'll write the final answer here. And 3 times 2 is just 6. And that is the answer to this problem right here. Once again, PEMDAS, take care of the parentheses first or brackets first, and then take it from there. Okay, which number is not odd? That one's really easy. That's clearly odd because it's not divisible by 2. That's how you know something's odd, is if it's not divisible by 2. Is this odd? Yes, it is, because it's not divisible by 2. Is this odd? Heck no, because it is divisible by 2. Done. Okay, so pi does not belong to what group of real numbers? Well, once again, we had that chart before, and I'll recreate it right now. Real numbers, yay. And this is irrational numbers. We'll call it RRAT. So pi is definitely in there, right? And then we have rational numbers over here. And I could keep going with the other circles, but at the end of the day, we're done. Pi does not belong to rational numbers, any of them. So the answer is rational numbers. Pi does not belong to rational numbers. Okay, so once again, we have this bracket scenario. PEMDAS would suggest that we should take care of this guy first. Now we have a fraction divided by another fraction. So on the next line, I'm going to write 1/6 times, that is times right there. Keep, change, flip, we have 5 over 12 times 6 over 1. Okay, so that becomes 1/6 times, let's just multiply straight across. So we have 30 over 12. Now, 30 over 12 could most definitely be reduced because this is divisible by 6 and this is divisible by 6. So we could rewrite this as the following. This could be rewritten as 1/6 times, 30 divided by 6. Once again, the LCM of 30 and 12 is 6. So 30 divided by 6 is 5. And this 12 divided by 6 is 2. So at the end of the day, we have 1/6 times 5 over 2. We can multiply that straight across as well, and that becomes 5 over 12. Because 1 times 5 is 5, and 6 times 2 is 12. And that cannot be reduced anymore, so this is actually the answer. All right, how many different kinds of numbers relate? How do the different kinds of numbers relate to each other? Well, that is once again the chart. So if we want to know how the different numbers relate to each other, well, we could call these the real numbers. I'll write it on the outside this time. We could call, maybe make 2 circles right out the gate, because hopefully my students getting the hang of this by now. These are the irrationals. All right, it's like pi, it's like this. Also, I'll throw in another one. That's irrational as well. And then over here, we have the rational numbers. Rational. And that consists of, things like 0, like 0.75, like 0.6 repeating, etc. And then inside that we have we would have another group of numbers called integers. And that's like -1, 0, 2, 3, yay. All of what would be the tick marks on a number line. That's integers. Inside integers, we have whole numbers. Whole numbers. And that is all of the positive integers, including 0. So that would be things like 0, 1, 2, 10, etc. And inside the whole numbers, you have another set called natural numbers. And that is literally all of the positive integers and all the positive whole numbers, well, all the whole numbers, except 0. 1, 2, 3, 4. So that is how that works. All right. So this is actually a decent way of understanding how all the numbers relate to each other. All right. All these real numbers, and you've got two kinds of real numbers. You've got irrational and rational. Irrational is all this stuff. If the decimal was to be laid before you, you would see that it would be a decimal that goes on forever and never repeats. Over here we have rational. These are numbers that could be represented as a over b, with a being an integer, b being an integer. It is such that if it is a decimal, it either stops like 0.75 or it repeats forever in such a way that there is a pattern. One particular kind of rational number is integer, and that is -1, 0, 2, 3. These are all the tick marks on a number line. A special kind of integer is called a whole number. That is all the positive integers, including 0. And then a special kind of whole number is natural numbers. That is literally all the positive integers, not including 0, because 0 is neither positive nor negative. Okay, so is it possible in the real world to have a square root of a negative number? Explain your reasoning. Okay, well, the answer to that is no, and here's why. Let's kind of put this off to the side, square root of -4, and be like, is this possible? Could we have a square root of a negative number? Well, let's be clear on what would otherwise be a normal situation. So the square root of 4 is definitely plus minus 2. Okay, so in other words, the square root of 4 is either positive 2 or negative 2. Now, why is that so? Well, the reason that's so is because square rooting something, taking the square root of something, is the opposite operation of squaring something. So one way that we can know for sure is we could set up this scenario where it's like 2 squared equals 4, right? And that checks out. 2 times itself equals 4. Right? We could also see very clearly that -2 squared also equals 4. Okay? So the square root of 4 is positive 2, denoted by here because positive 2 squared equals 4. And the square root of 4 is also -2, denoted here by remembering that -2 squared equals 4. So when you ask yourself, what's the square root of 4? That's another way of saying what times itself would give you just a 4. All right. Now, in case that's not clear, let's investigate another scenario. What is the square root of 16? Well, that is like saying what times itself gives me the 16. Well, that would be positive 4 or -4. How do I know? Because positive 4 times itself gives me 16. -4 times itself, -4 times another -4 gives me a 16. Okay? So that leads us to this question. In the real world, can we have a square root of a negative number? And the answer is no, because there is nothing times itself that would give me a -4. Because think about it. You might say, well, what about -2? Well, -2 squared gives me a positive 4, because a -2 times a -2 is a negative number times another negative number, which gives me a positive number, right? And then you could be like, okay, well, what about positive 2? Well, positive 2 squared also gives me a positive 4 because a positive number times itself is a positive number times a positive number, and that's going to give me a positive number. So there is no number times itself that would ever give me a negative number. Once again, I'll say it. There is no number times itself that will ever give you a negative number as a result. Okay? So these do not check out. There is no number times itself that would give me a negative 4. Impossible. All right, so we have the final problem. We have a bracket divided by another bracket. So as usual, according to PEMDAS, we're going to have to simplify these guys. So let's take a look at the first bracket. First bracket, multiplying straight across 1 times 5 is definitely 5 all over. Multiplying straight across 5 times 7, well, that is 35. So that's 5 over 35. And let's just leave it there for now. And that's going to be divided by, let's see, 2/7 times 1/2. Well, let's investigate that. Still using PEMDAS in the sense that we're dealing with the parentheses first. So 2 times 1 is just 2 all over 7 times 2, which is 14. Okay, now, still kind of simplifying what's inside each parentheses first. So on the next line, we're going to ask ourselves, is 5 over 35 a fraction that can be reduced? Absolutely. 5 and 35 both have a least common multiple of 5. 5 divided by 5 is 1, and 35 divided by 5 is 7. So that could be reduced to 1 over 7. So that's going to be 1/7 divided by whatever this guy reduces to, 2 over 14. That's definitely reducible. 2 and 14 have a least common multiple of 2. 2 divided by 2 is 1, and 14 divided by 2 is 7. So let's investigate this scenario. You have 1/7 divided by 1/7. Okay, well, let's do keep, change, flip. Let's just do that. Let's just go right to the old strategy that we know works every time. So that's going to be 1/7 times the reciprocal, which is 7 over 1, right? So multiplying straight across, we end up with 7 over 7, right? Because 1 times 7 is 7, 7 times 1 is 7. So we have 7 over 7, and that is equal to 1. And that's the answer. All right, so I hope that was helpful for my student who's watching it. I hope that's helpful. Obviously, there might have been moments where I moved too fast, but remember, you can always pause the video, you can always rewind the video, and you can also even slow down my speech on YouTube. You could also speed up my speech on YouTube too, which might actually be more useful. All right, because if I'm going over a concept that you feel like you already know, well, you just speed it up. All right. Anyway, good luck to my student, and good luck to any student out there who could find this information helpful. And I will see you next time.